I'm sitting here, I am just amazed. I mean, I know I've been mad at my computer a bunch before this year, but I am amazed at how much stuff is going on. Look, this is track 3 getting loaded. This is track 4. This is track 5. This is track 6 that we just did, and this will be the end of it, track 7. I just want to introduce the energy thing. So we looked at the contracted length and we did all that. So suppose one pair of identical, what's wrong? But wait, from her frame, the Earth was moving with respect to her and her twins. What's wrong here? The answer is that the traveling twin, in order to return to Earth, has to turn around and come back. Therefore, her frame is not inertial, and she is indeed younger than her twin when she comes home. In other words, she's in an accelerating reference frame, so she gets back quicker. All right, now we're going to talk about relativistic kinetic energy and total energy and the mass energy equivalence. You can already see we've got a kinetic energy here, which is gamma minus 1 times mc squared. Oh my gosh, we are getting close. We are getting so close to one of the most famous equations of all time. Probably the most famous one that nobody knows what it means, but you're going to know now. All right, so relativistic kinetic energy. There's the equation. Now look, classically, when they knew they had a problem when they were doing all this nuclear physics back in the early 1900s, okay, because the subatomic particles were behaving very funny. They weren't following. They were making predictions based on this. They applied Einstein's thing, and then their predictions started making sense. And this is what Nick was asking in class earlier. What happens when this thing gets closer to, and when vehicles, it reaches it doesn't get there. It goes to infinity. All right? The energy goes. That is why, to try and get anything bigger than a photon to go the speed of light requires all the energy in the universe, because the energy goes to infinity. Okay? It's impossible. All right, so, and here's the momentum. Relativistic momentum is then this. All right, and here we go. The total energy then in a system, note that this is not 0 when V is equal to 0. When V is equal to 0, when V is equal to 0, you just have the rest energy. When V is equal to 0, you have the rest energy of E equals mc squared. Okay? So look, you got the gamma function. It's gamma. The total energy in the system is equal to this. All right, so let me show you what's going on here, and we'll do one. And this is where we're going to start on Monday, is we'll work with the example. But here's the deal. All right, so you've got the total energy of the system, E, is equal to gamma times the mass of the system times c squared. Okay, if it's traveling along, that's the total energy. All right, and we know that the total energy is equal to the kinetic energy of the system plus the rest energy. All right. Okay. So we know we've got this. We've got gamma mc squared is equal to the kinetic energy plus mc squared, because that's what the rest energy is. All right. So look, this is why they got the kinetic energy then, a little swappy changey here. Gamma minus, so I've got gamma mc squared minus mc squared. Factor out the gamma minus 1 times mc squared. So it's easy when you're working with the and the relativistic momentum is equal to gamma mv times the speed. Now, this one gets up here. These are easier to work with because you know what? We're going to use electron volts. And it makes it much, much easier to work with because these are all small subatomic particles that we're dealing with for the most part here. Okay? So we use electron volts to make this much, much easier. All right, and I think that's what they do in the slides here. No, they don't. They do it in the text. All right, so I'm going to have to do it here. All right, here's the deal. Here's the deal. Let's figure out, and then this is where we'll start on Monday. Okay. I'm going to go ahead and stop this, and then we'll do a track 8.